So I'm really very happy to be here. And Nick said I could talk about anything I wanted to talk about. And so that was sort of a really hard thing to wonder about. I was thinking about giving a little bit more research-oriented talk. But then he told me that you really hadn't covered mobility in the course. So actually I watched Phil teach the wireless part of the course, watched his videos online. But you haven't talked too much about mobility. And so I thought, gee, you know, if there was one thing looking at what you've covered this semester, and I say, gee, what's missing there? It's actually mobile networking, and it's an area that I do some research in. And so given the opportunity to talk about anything that I could possibly talk about, I thought something fun to talk about would be mobile networking, and so that's what I'd like to talk about today. So I want to convince you, first of all, right, before you start a class and before you study a topic, you should be convinced that it's interesting. And I want to, in this slide here, sort of convince you that there's almost nothing else in networking that you should be more excited or curious or thinking about than mobility. And the reason's the following. We're sort of at this inflection point now. If you go back, way back to the days of the dinosaur when Nick was a graduate student, everything was wired, right? And it wasn't even, well, it was Ethernet back then, but barely, right? Right. And now if you look at how are devices, how are hosts connecting to the internet, you've got, well, first of all, many more, just thinking about phones, way more wireless phones than wired phone subscribers now across the world. And we hit an inflection point somewhere in the last 2 years where now the number of internet-connected devices there are more wireless than wireline. So you think about all the kinds of devices that I'm sure you all, I see some of you using them right now, are using to connect to the internet. So the notion that, I've got this machine, it's got a blue Ethernet cable coming out of it and connecting me, to a switch, to a router, that's sort of the way things used to be. And if you look at how the curves are changing, right, numbers of wireless devices going like that, number of wired devices going like that, we've passed that crossover point already. And if you look at the derivatives, the number of wireless devices is just going to be increasing even faster, right? So we've passed this really important point. And so the question is, okay, so we've got all these wireless devices. We've got an internet architecture that was created actually quite a long time ago, right? Look back at the early TCP/IP RFCs. They're from the early 1980s. That's when everybody was connected over wires, right? So life has changed, and yet we've got an architecture that is sort of designed for an earlier era, maybe, is one way to think about it. Okay, so hopefully that's enough to at least get you interested that maybe there's something here. So let's start off, wow, chalk. I haven't seen chalk since I was a kid. All right, what does it mean to be mobile? Okay, so from an internet perspective. So are you mobile? You think you're mobile? Say right now? So I talked to somebody who taught one of these, or did one of these Thursday classes with you folks, and she promised me that there were 4 or 5 people who you could always count on in this class. I don't know which of you she was talking about, but I know you're out there, right? So anybody here feel mobile or not mobile? Yes?
When I sit in gates and I use the Wi-Fi, I have one IP address. And then when the Wi-Fi flakes out on me and I turn on my MiFi, I have a completely different IP address.
Okay.
Where I think I'm in Colorado.
Okay. Oh, cool. Okay. So you're in one place, but you have different addresses. Okay. So I guess I'd argue from that point of view, you're definitely mobile, right? You're physically sitting there. But from an internet perspective, all of us, you're moving from your Gates connection to some connection in Colorado, right? And if you even think about what you did this morning, right? Most of you probably got up and the first thing you did was you looked at your Facebook account or read email or whatever you do in the morning, right? And you probably did that from your dorm, right? So you got an IP address out of your dorm from DHCP. You did some stuff. You went and had breakfast. You went to a class. You connected. You read The Onion or whatever you do in class. And so your internet address kept changing then. Not quite like Colorado, from Palo Alto to Colorado, but it kept changing, right? So I guess the first thing to think about is that, exactly the point that was raised, that your internet address can be changing. Even though you're sitting there and you don't maybe feel very mobile, right? Maybe you want to get up and run out, but even though you're sitting somewhere, you're going to get up and move. So we have to worry about this question about what's the time scale over which you're changing your point of attachment into the internet. Okay, so I want to argue then that even you now sitting, in some sense, you're mobile. You're not physically mobile. So how about me? So I'm walking around, and if I weren't tethered here because of the display, I'd want to walk around, and you'd probably say, oh, I'm mobile, but from a networking standpoint, I'm clearly not mobile, right? I'm attached to some access point, wherever it is. I don't see one in the room here, but there's one nearby. So even though I'm physically mobile, I'm actually static right now, or I'm immobile, right? So I guess the second thing then is that physical mobility doesn't imply network mobility. I'm having so much fun writing with chalk that I may keep going, right? So that's another aspect of mobility that we want to think about. And then lastly, I'll go out to dinner and I'll probably call home and talk on the phone, and I'll be driving, and maybe we'll all agree then that that's actually something that's definitely mobile. So when we think about mobile, it's not an easy question, right? There's all different kinds of mobility that we want to talk about. And so all the way from this notion of sort of very low mobility, and you read something in the morning from your dorm room, then you go to a class, you go to another class. That starts to bring us over to here, where you are moving during the day, you're connecting, disconnecting from the network, you're using DHCP to get addresses, all the way to me over here, zooming around in my rental car, talking on my phone, reading my email while I'm driving, all that kind of stuff. Okay, so there's this whole range of mobility that we're going to have to accommodate if we want to talk about mobility. Okay? All right, so actually I hear this is your last class, so congratulations on that. It's a perfect time to reflect back on everything that you've learned this semester. I know things are slightly different here, right? So think back about all the kinds of things that you've learned so far, and now imagine this notion that I'm changing my point of attachment from one part of the network to another. What are the kinds of things that, given that we've got mobility, sort of this spectrum of mobility, what are the kinds of things that we're going to need to handle? I'm not going to ask you to define a protocol, just sort of in a broad sense. What are the kinds of things you think we're going to have to deal with here? Yes?
Probably want to ensure that you have uninterrupted flows.
Okay.
So you would need to know, based on where somebody's point of attachment is, how to actually route the traffic.
Great. So I definitely want uninterrupted. I'm a bad speller. Uninterrupted flows. Okay, so that's a definite, right? As I'm moving around, I want those packets to keep coming to me. Okay? So that's not going to be magic, right? They're not going to. It's not like I'm magnetic and they're just going to sort of follow me around, right? So I'm going to need some other infrastructure. In addition, that's what I want. What are some other things we might need to do to support that? Yeah.
Smoothly changing your IP address and having the other endpoint be aware of that.
Okay. So as a fact, I'll have a changing IP address, and I think you also said I want the other side, like the sender, to know about that.
Yeah, the other endpoint.
Okay.
Be aware.
I want the other end to be aware. Okay. Everybody agree? So that's the notion about whether or not the other end needs to be aware is maybe true, maybe not, right? Maybe I don't want the other end to be aware, right? Wouldn't it be cool? Matter of fact, if I'm, think of a cell phone, right? I could start a conversation with you, and I could then start driving to Los Angeles and have a phone call with you all the way to Los Angeles, and you have no idea where I am, right? And so maybe, I'll put this down underneath it. Maybe I want the other end unaware of my mobility. Maybe for privacy purposes, but maybe why do you want a sender to have to deal with the fact that, oh, your address just changed, maybe I better send you a new, maybe I better readdress my packets to you at a new IP address. So I think we'll see that you can actually have it either way. Okay? Any other thoughts about, so this is uninterrupted flows. That's absolutely what we want to do. We're going to have changing IP addresses so that somehow we need to deal with this, right? This notion that our IP addresses are going to be changed. And it turns out that this is one of the things we're going to have to worry about the most. Okay? Let's see, I forgot what, So this is actually a mechanism for dealing with this. If I'm going to be moving and somebody has to send me stuff, somehow if I'm moving around, either I or an agent working for me is going to have to say where I am so that other people can look me up and locate me. Okay, so we'll need that kind of function. We'll need to send, as was mentioned here, to the recipient, not at a usual address, right? I'm changing my address, so maybe there's this notion of what's usual. And then, absolutely exactly what was said there. The network needs to somehow make sure that packets get to the recipient who's in motion. Okay? Anything else? Yeah?
Changes in RTT, and if the network path has different pathing.
Oh, that's great. So changes, so I have to maybe accommodate changes in RTT. Okay. Wow, really nice. There's a question of whether we want to do that at the application level or the network level, but that's actually something I hadn't really thought about. Another thing? Yeah.
So, I guess I have kind of a jump start on this, working with MPTCP, but maybe like instead of just uninterrupted flows, like have more than one flow per connection.
Okay. So I could use multiple flows per connection to allow me to help with the uninterrupted. Yeah, absolutely. And matter of fact, when we get to the questions of handoff, we'll see exactly those kinds of behaviors, right? So that notion of maybe having multiple flows would be a way of dealing with this. And if I got multiple copies, that would be okay because I can already get multiple copies in any kind of best effort service. So maybe I can deal with it. Yep.
Speaking of new protocols, it would make sense if you're in a mobile environment to not necessarily have a hierarchical structure for the way IP addresses are assigned. Maybe you want things to self-identify, and you want a mesh network to create itself so that you can have multiple flows over different local devices.
Okay. So that sort of, I think, so I agree with you 100%. I think that takes us out of the realm of CS144, but I'll agree with that 100%. So I don't know whether that's covered in CS145 or whatever the follow-up course is, right? But so let's say unstructured networks. So ad hoc networks. And those could be self-organizing, self-assembling, all sorts of things, right? Without that sort of traditional hierarchical structure. So absolutely. So that's not actually something that I was going to talk about at all today, but that's okay. I mean, you're 100% on. Anything else? It's always nice to get answers you don't expect. Actually, it's great. Okay. All right, so I guess one of the things I want to do, and maybe I'll try to remember this changes in RTT, because I like that a lot. I want to sort of just now go through some of these things that we've talked about and just try to explore those a little bit deeper. What kind of mechanisms are we going to need to look up and register, to send to someone not at their usual address, and to sort of ensure this smooth flow of packets? Okay, so I'm a big fan. As a matter of fact, I think I've probably written it in the book, our textbook, multiple times. I'm sort of a big fan that any networking scenario you run into and you need a protocol, humans have solved the problem already, right? And they've probably solved it pretty efficiently, right? And so this is the lookup problem. So imagine you need to locate a mobile friend, and so consider a friend who's frequently changing her address. In this case, these were the icons that we had originally in our textbook, and we sent it into the editor, who said that they were just too, I don't know. They got very blandized by the editor because these were too, I don't know, a nerdy guy and an innocent-looking girl. They didn't like that. Anyway, imagine this nerdy-looking guy wants to, find his high school sweetheart, right, who he's lost touch with, right? Or imagine you want to do that. Okay, so I've got answers there, but I'm actually very interested in how you would go about doing that, right? And then I'm going to ask either Nick or Phil. I'm going to probably ask Nick because he's older. So it's a problem in real life. What would you do?
Find it on Facebook.
Facebook. So that's an obvious answer to all of you, right? But to me, it wasn't at all obvious until the last time I taught this course, and my entire class shouted out, Facebook, right? And nobody had any other clue about how they would find the friend. Okay? Okay, so Facebook. All right. Any other? Yeah. Okay. Talk to who might know her, or ask a friend who knows, right? Or a parent, somebody. Sorry, I know you can't see behind there, but that's okay. Ask a friend or a parent. Yep. Yes.
There are people search services.
Okay. Yeah, so it means somebody who's not on Facebook. Okay, so look up like a white pages search. Okay. Yep.
Might try her last known address.
Wow, good one. I hadn't thought about it. Last known address. That's a great one. And actually, for a postal service, right, if she's registered where she's gone, it'll get to her, right? Yep.
Court records.
Another new one. Okay.
We know something about your friend.
All right. Yeah, public records. We'll just say public records, right? All right. Okay.
What I was going to say, I mean, it's kind of the ask a friend. If it's a ex-school friend, then you probably know parents or school.
Yeah.
So it's kind of the ask.
Yeah. So for me, my first answer to this was always I'd ask her parents, right? Yeah. Because you know her parents, and unless they really don't like you, they'll. Well, here's an interesting question. What do you think the parents would respond, right? Would the parents say, oh, Mary's at such and such an address, here's her phone number, here's her, here's everything about her? Or would they say, well, yeah, I know, what do you want to talk to her? And then you'd say, yeah. And then they'd say, why don't you send it to me, right? Send me a letter and I'll forward it to her, right? So there's two very different kinds of information you could get back, right? You could get back a routable address, right? Right where to go to find Mary, or the mother, father could say, well, send it to me and I'll, I do promise, because I like you personally, I'll make sure she gets it, okay? And so in some way you locate her, certainly you can communicate with her, okay? So, Facebook, right there, okay? All right. Oh, yep.
I think a good analogy for that is an email address today, where often I don't want to give out someone's email address, but I certainly will forward a message along.
Right. So maybe one thing we should think about here is direct versus indirect, right? So you can either go to somebody directly or we can go indirectly. And matter of fact, when we take a look at how with mobile phones and the cellular network or with IP, with things like mobile IP, we'll see that this sort of distinction becomes very important, how we get there. Okay, so I don't know. I'll show you my answers to this. Actually, I put Facebook on. These were the ones that I had, so somebody said search online, right? Well, so for me, would I look in a phone book? I guess I'm sort of I used to be a paper guy. Call her parents. Maybe actually expect her to let you know where she is, right? So whenever she moves, she just says, oh, well, people do that on Facebook, right? Here's where I am, right? Or I look it up through Facebook. Okay, so I think I want to say that there are analogies to all of these things with mobility. Some of the things that we're going to look at, which we'll see later on in this class, about how this actually happens, actually gets to this heart of what was mentioned here by Phil, this notion of direct versus indirect. Okay. All right. So that's the lookup question. Remember, we've got lookup. We've got this question about how to send, and then how to make it smooth. Okay. All right. So that's the lookup. So routing. Actually, let's look at this thing right here. Direct versus indirect. Actually, before we do that, how about this as a solution, right? So you've all seen about how you can, right? You learned about longest prefix matching and things like that, right? So if I have an address, right, 128.119.164.114, right? That's my IP address. I could take that IP address and go into a new network, right? And that new network, using all the existing IP mechanisms, could now advertise that in addition to this /16 address that's associated with the network, that they also have this /32 address, which is me, right? And with no changes at all to any of the existing infrastructure, problem solved, right? Whatever the network I'm in says, oh, I am now the owner of this address. It's more, it's longer than anybody else who's advertising a UMass address, and so routing works, right? So let the routers advertise the permanent address of a mobile node in residence, right? So I come to Stanford. Stanford says, I don't know offhand what your IP address is, but you've got a /16. It says, all these /16s route to Stanford, and by the way, this 132-bit UMass address also routed to Stanford, okay? And, so that might actually work, right? The routing tables then, all throughout the internet, are going to know where to reach me because Stanford's now advertising my UMass IP address. No changes to end systems. This question about who knows about whether you've changed, these questions sort of become irrelevant, right? Because I still have my IP address. Sound okay? Oh, I saw somebody say yes, but you were yawning when you said that, so that's not a good sign. Sounds great. Okay, well, it works, right? It would work, right? But the question is, I actually have millions. That should be billions. Sorry, put a B. Put a B there. What happens when we've got already several billion mobile users, and now you want to start flooding throughout the routing system? Where each of those is, each of those individuals are. That's the right English there. Okay, so in general, although one might ask, if it were millions, could you do it? If it were hundreds of millions, could you do it? Where does that break? Where does this idea break? But generally, this is not an avenue people have gone down. Okay, so if the network's not going to do it, and we've got problems like this that we want to worry about, then the other thing is we could let the end systems handle it, right? And so we've actually already identified two ways of doing that. Here, indirect, this is sort of, I need to talk to Mary. I'll send it to Mary's mom, and Mary's mom will forward the message to her. So indirect routing, communication from me, the correspondent, to the mobile goes through the home agent, or something called a home agent, a mom, somebody who knows, didn't write that down, somebody who knows how to find the person you want to talk to, or direct routing, where maybe now I query Facebook or court records or something like that, figure out where my friend Mary is actually located, and send directly. Okay, and we'll see that these are sort of the two basic approaches historically that have been taken. All right, let me stop there for a second, and I think it's always good to stop and just see if there are questions or comments. Looks okay? Okay.
You said, I thought you were going to add on the first one about letting the routing handle it.
Uh-huh.
There's all sorts of security implications or spoofing and saying that I now own the address that I don't.
Ah.
There'll be all sorts of other practical difficulties other than just the
Right. So of course Nick is right, but he's righter than he even realizes. Right. So he brought up the security issue. Right. So here, I mean, think of all of the things that could go wrong here if you get somebody malicious. Right. So clearly here, what Nick was talking about here is somebody maliciously reporting that, oh, this particular IP address. Right. So I don't know. Somebody from Berkeley saying, oh, Jim is in Berkeley right now, right? And injecting that in, right? And so everything gets routed to Berkeley, and then lo and behold, I'm not there, right? So I'd get my traffic would get black holed. The same thing actually happens here, right? That when we get to registration, like what if, I'm sure there are scams like this on the internet, right? Where, Mary says to her mom, oh, you know what? I just left Atlanta and I'm in Chattanooga, right? But of course it's not Mary who says that, it's somebody else, right? So think of all of the ways that you can inject false information into a system like this, whether it's indirect, whether it's direct, whether it's this, right? So I think with location-based services, it's something you need to be extremely careful about, right? Okay? All right, so a little bit of vocabulary here. Just so that you'll be versed in when we start talking about mobile IP and cellular networks, sort of the common vocabulary. All right, so there is a notion that you've got maybe a permanent address, right? So you've got an address in a home network, and it can be always used somehow to reach you, at least initially. Okay, so here's my home address, my permanent address. I've got a home network, something I belong to. It's sort of my normal the comment that was made earlier that, oh, you're in Stanford and then all of a sudden you're connected to Colorado in that case. So you've got a home network that you belong to. Even better than that, you got a mom, right? Or a dad or somebody who's watching out for you. You've got a home agent, some entity, some piece of software that's going to perform mobility functions on your behalf if you're not in your home network. Okay? So we'll see, a very interesting thing, I think we tend to, in the internet world, we tend to poo-pah the telephone network. Actually, because, I don't know, it's slow, it's big, it's inefficient, it's whatever. They've actually done a lot of things pretty cool and pretty well. And, a lot of the mobility things that we'll talk about in the IP world have their exact analogy in the cellular world. And they did that a lot earlier. So we'll see that in a second. Why did I say that? It'll come to me. Okay. Well, actually, I know why I said that. I said that because this notion of a permanent address, a home network, a home agent, we'll see this in mobile IP, and we'll also see it in cellular systems as well. Okay. Also in cellular systems and in mobile IP, we'll see the notion of, well, who's the person who's doing the sending? There's going to be a permanent address that you keep. A notion of a care of address, right? So this, in a sense, is when you move somewhere outside of your home, this is like a temporary address that you'll get. It's in your visited network, so there's a network that you're visiting away from your home. You come into a visited network, and that got cut off, but there's a foreign agent. So remember, you've got your home agent over here. You've got a foreign agent over here this is a piece of software in the visited network that's going to help you out, right? It's going to register you and do stuff like that. Okay, so just some vocabulary. Let's now start with the registration process, and then we'll talk a little bit about the routing. And then what I like to do is just sort of finish up and talk specifically about mobile IP and how mobility is handled in cellular systems. Okay, so if I register, well, the protocol's pretty simple here. What I need to do is I show up in a network here. So what's going to happen? I'm going to contact, somehow I need a discovery protocol, right? I've got to find this foreign agent, but we know how to do that. Matter of fact, we'll see how to do that in mobile IP using some existing mechanisms for router discovery. So I find a foreign agent, mobile contacts foreign agent entering the visiting network. This foreign agent is now going to talk to my home agent and say, oh, Jim is now in this visited network, right? So now my home network knows where I am. Okay, so foreign agent contacts home network, says this mobile's resident in my network. Okay, fine. And as an end result of this sort of very simple registration process, the foreign agent knows about the mobile, right, over here. Foreign agent here knows that I'm there, I need to be taken care of. And the home agent knows the location of where I am. Okay, so matter of fact now, if anybody tries to send me stuff at home, you can sort of see what's going to happen here, right? At least if we use this indirect routing. If I send stuff to Mary's mom, then Mary's mom is going to, send it over here to where Mary is. Or, alternatively, if we take this direct approach, meaning you as the correspondent correspond directly there, the correspondent is going to say to the home agent, where's Mary? Get an answer, and then go over there. Okay, we'll see that both of those are possible. Okay, so indirect routing, this is just sort of some diagrams sort of showing this. The correspondent addresses packets. So here's the correspondent. Send to Mary. So addresses using the home address. Okay, the home agent here. So Mary's no longer here. Mary's here. The home agent knows that. The home agent intercepts the packet coming in, sends it over here. The foreign agent receives this on behalf of Mary and then delivers the packet to Mary. Pretty simple. Then, of course, now Mary can reply here, coming back here, and then now there's a question. What do you think the source address of stuff coming from here ought to be? Right, so remember, initially, to contact Mary, we sent it to Mary's home address. Mary's home address sent it through here over to the visited network. The visited network delivered it to Mary. Mary now replies back to this IP address. Let's say we're doing IP here. What do you think what's the source address that one might want to use there? How come? So common is have to use the home address. Right, exactly. So when the first packet went out here, I mean, imagine trying to do TCP, right? And you're trying to set up a connection, and it goes over here, and a reply comes back here. Well, the initial SYN that you sent out had this home address here, and if it comes back, with an address over here as a reply to that SYN, something's wrong. Anyway, it wouldn't be transparent, right? So if I want to keep that transparency, this address coming back here has to correspond to this, right? Or I could give up transparency. Yeah.
Start sending stuff to that address instead, to the visiting address. And then what if you move again? Now you have another problem.
Exactly, right. So even if we could make this work for this one time, imagine what happens now when this one moves here, and now I'm here and I'm sending stuff there, and then all of a sudden this one the remote gets a new address and starts sending new things here. I think we could make that work, right? Like, oh, I'll detect it. I'll have a protocol that says, oh, did you move? And what's your new address? But it's going to be ugly. What's that?
So
You
there will probably be some period of time where you're trying to send something to something.
Right. So we might violate this uninterrupted flow smoothness
Yeah.
condition. I mean, we'll see that that's going to be an issue even if we do something like this, right? Because you're going to get these race conditions. Imagine that we move from a network here to a network here, and we re-register back here, right? So there's going to be some time where packets might be in transit here, but I've moved and there's a registration. So yeah, I'm going to lose some packets. You know, the beautiful thing about a best effort service model is who cares, right? It's almost like, oh, the packets got lost because they got dropped here, right? It doesn't matter whether they got dropped because of some really complicated mobility and race condition, or whether they just got dropped here because of some bit errors, right? One of the real beauties of a best effort service model is that it forgives all kinds of sins and makes life really easy, especially for something calm or complicated like this. It works okay. Yeah.
Like Verizon's infrastructure would have both contained within it, or is it kind of a separate?
Okay. So I'll answer that question just a little bit later. But your home agent, if you're talking about cellular, since you mentioned, well, Verizon does both, right? If I think about a phone network, you've got an agent in your home cellular network, and then if I'm within AT&T's footprint, there'll be something called a visitor or location register, which is the equivalent there, right? So each one has its own infrastructure. You've got something in your home that takes care of you, and every network you go into is going to have its own to do that registration for you. Was there one other comment? Oh, yeah.
I think this also plays badly if I think it's ingress filtering. If you have a router
yeah, right.
ingress filtering, it's going
Right.
to say, yeah, it's not for my subnet, so I'm not.
Sorry, egress filtering.
Egress.
Right, yeah. Right, so if I'm doing egress filtering here, and now actually, egress filtering is going to be a problem here, right? Because if the address being used here is this one, and I'm doing egress filtering, and I haven't somehow tied in mobility, then nothing's going to actually make it through there, right? So one would have to worry about that, right? Yeah. Good point. All right, so this is indirect routing. So just a few comments here to note. So we notice that we've got this permanent address, and for all those good reasons that were mentioned, if we use indirect routing and go through here, we get transparency. We avoid a lot of problems. So that's probably a good thing. We have this care of address. We saw that before. I have this running argument with a colleague of mine whether this is important. He thinks it's really important. I say it doesn't matter. But there's actually been a lot of work done on this notion of triangle routing. So let's say that Nick and I are traveling in France, and I want to send something to Nick, and I go through Stanford, right? So it comes all the way, and we're like in hotels a block from each other. It goes all the way back to the US, to Palo Alto, and then all the way to him. So, you could send to somebody literally physically next to you and have to go all the way around the world to actually reach them. And some people think that that's a problem, and maybe it is. But this is called the triangle routing problem, that if these two people are close to each other, you still have to go through this home location. And if this home location is far away, it can be inefficient. Yes?
It's not just inefficient, but like if the link between the U.S. and France is somehow down, or there's some disaster, like this just happened to me the other day.
Yeah, okay.
When Sandy hit New York, my home cell phone is in New Jersey, and people couldn't call me at Stanford because my traffic was getting routed through Jersey. Yeah,
so I mean that's a good point. The comment is that if you're using more of the infrastructure, and if this infrastructure is broken, so imagine these two are really close to each other, and this is you needed to go through New Jersey, and there was a break in this link or this link, and these two are both in California, then yeah, it's absolutely a problem. And so you you actually do have other, if you could find other paths, that would be a great thing, right? And if this got disconnected. Yeah, so maybe it's not just performance. Yeah.
I may not care if it's email. In fact, probably Gmail is doing this already, right? So
right.
It's going through it somewhere else. But if we're having an interactive Skype conversation, then it actually might be noticeably different depending on actual behavior of the application might be quite different.
Yeah, right. So, I mean, if I do have to go all the way around the world, even if I'm doing, right? Maybe, right. It's getting close. If you have to go all the way around the world, it's a couple 100 milliseconds round trip. Right. Yeah. So I don't mean to poo-poo that. Maybe I poo-pooed it too much. Anyway, I like to argue with my friends. So, all right. All right. So actually, I think we talked about this issue already. So indirect routing. Now let's say I move between networks. This is this scenario where this user now moves to another network. Okay. So you can see the problem, the layers of how this problem can get harder and harder. So suppose the mobile user moves to another network. Here's what I would do in sort of the straightforward case, right? I'd register with a new foreign agent. So I show up. I go from the Stanford network to that yogurt place I go to all the time downtown, and I register there, and then they, inform UMass that I'm in downtown Palo Alto rather than on the Stanford campus. So the new foreign agent registers me with my home agent. The home agent updates my care of address, so now UMass knows I'm downtown rather than on campus. Packets continue to be forwarded to me, but with a new care of address, so I'm in downtown. We talked before about, some packets could be lost here, right? Because I leave Stanford really quickly. I go downtown. People are still sending packets to Stanford, but I'm downtown. Yep?
How does the home agent track the user?
How does the home agent track the user? It's not, let's go back to this picture here. Right? It's not the home agent that tracks the user. Well, the home agent does know where the user is. So in that sense, yeah, absolutely. The home agent, that information is pushed to the home agent, right? Because when I move, I don't have a picture of this. When I move from here to here, or when I show up here, the fact that I'm here is being pushed from remote to home. And when I move from here to here, some other network, that new foreign agent will send a new message over here saying Jim is no longer here, Jim is down here. Okay, so the tracking, it is tracking you, but the state updates are always coming remotely, right? So it's not like, I don't know, I've got a GPS tracking device, or I rely on these foreign agents to always be updating where I am. Okay, and you can again see the possible security, all the security problems that could happen if you allowed just any foreign agent to say that you're in their network. Okay. Blah, 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 blah. Okay, so packets continued to be forwarded to me with my new care of address. This was the case that I moved. Mobility, changing foreign networks are transparent, right? Ongoing connections can be maintained. Maybe with some dropped packets, but again, with a best effort service model, TCP for reliability, those packets eventually get to me, as long as it's not too many. Okay. Okay, so that was indirect routing. Direct routing. Okay, so how does this work? Remember, these were the two things that we identified. Not me, actually. One of you identified direct versus indirect at the beginning of the class here. So here's one way this could work, right? So the correspondent says, tell me where Mary is. Mary's mom in the home network replies back to me, says you could find Mary here. I then now have Mary's address, and so I correspond, directly with Mary, and Mary replies back to me. So that's sort of a direct way of doing it. Some comments here. Well, first of all, it overcomes the triangle routing problem, right? So we don't, although you do have to go to the home to figure out where somebody is, then you correspond with them directly. So that gets over the New Jersey problem of links being broken here or something like that. But it's non-transparent to the correspondent, right? And so exactly the question that you brought up earlier. So I query Mary's mom. Mary's mom tells me where Mary is. I talk to Mary. Mary moves. How do I deal with that? That's the hard part if I do direct routing. So I need another protocol. I need some other protocol for Mary to signal to me that she's changed her address. Here's the new address. And it starts getting messy. Wow. See? It's starting to get messy. The reason I put this up, actually, is because it'll give you a preview about a little bit about how mobility works in a cellular network. So imagine I'm talking to Mary. I talked to Mary. Mary's mom. I talked to Mary's mom. Mary's mom told me where to go. I sent something to Mary here, right? Because that's where she was. And now Mary moves from here to here. And I just said, oh, we need a protocol for Mary to tell me that she moved. Well, maybe I don't need that protocol. Maybe I can make that mobility transparent. And the way I might do that is Mary moves from here to here. I continue sending packets to this foreign agent where Mary first showed up. This foreign agent is told by this foreign agent that Mary's now here, and so the packets sort of get deflected down here and routed to Mary. So actually, as we'll see when we look at cellular networks, this notion of an anchor foreign agent is something that's used to route your telephone calls as your mobile. Yeah? I've reintroduced the triangle routing problem. I'm not sure it's the triangle routing problem. It's getting ugly, right? Because imagine now Mary goes to multiple networks, right? And now Mary goes to 10 networks, right? Now I go to the anchor, and the anchor forwards to a forwarder, who forwards to a forwarder to a forwarder to a forwarder, right? And the decagon?
Decagon, yeah, 10. You've got 10 sides.
Oh, right. Instead of the triangle routing, it's a decagon routing.
Yeah.
Pardon me?
The example was driving from San Francisco to LA. So
right.
if you wanted a constant phone call the whole way there, you have your anchor somewhere in San Francisco, and now you've got a triangle. You could be calling someone in LA, and your traffic's got to go all the way up to San Francisco.
Oh, okay. Yeah, you're right there. Even worse than that, I don't know the names of any towns. I live on the East Coast, so I don't know the name of a single town between here and LA. But
Santa Barbara. In Santa Barbara.
Oh, I know where Santa Barbara is. Right? That's close to LA. So you could have that triangle routing problem. But I think what's even worse is that now you've got packets sort of following you through a series of 10 or however many routers. And you may think that this sounds ridiculous, but in fact it happens in the cellular network. And there's actually protocols for once you get to some number, like 6 or whatever it is that the network, that particular provider wants, you've got this whole signaling protocol that says take out all of these 9 and route directly from here to me down here in LA. So I want to say it's ugly, but I never like to say bad things about the phone network. So it's complicated. That's a fair thing to say. Oh, sure.
So instead of intermediary steps, then directly connect it, why not just if each time you have this new foreign agent, then reroute it so it's directly connected?
Yeah. So that's actually how you would actually do it, right? That every time I moved, and I think that's the way it happens in the cellular network, you have an opportunity to do this shortcut, right? So rather than, you sort of do it on an event basis rather than a periodic basis, so that when I move to the 6th one, I'd have an opportunity there to do that connection. Just what you were suggesting, yeah. And I think, although I'm not 100% sure, that's the way it's done. Okay, so what have we learned so far? So we learned about lookup and registration, direct versus indirect routing, home and forward agents to help with mobility. Okay, so I'm very fond of saying to my students at UMass that if you remember 3 things from a class 2 weeks from now, I'll be very happy, right? And 2 weeks from now will be close to Christmas time. It'll be past your mid-final exams, right? So a lot of stuff will be flushed out of your caches, right? So if there are 3 things that you remember, here are 3 things that I'm hoping. I mean, the idea is just to sort of give you a flavor about architectures for dealing with mobility. So I think these are really the 3 key things. And matter of fact, all I want to do for the next 15 minutes or so is to tell you now, I mean, you've got all of the basic principles and techniques for how this is done in practice in these 3 things here. I want to take a quick look at how mobile IP does that, and then we'll take a quick look at how this is done in cellular networks. Okay? So actually, I want you to remember 4 or 5 things. These 3 conceptual things, and then how they're embodied in practice, which is sort of how I'd like to finish up here. Okay, so so mobile IP. It's got, again, here are the features. If you know these three things, you can look at almost any mobile system and say, yeah, I sort of see some of these reflected there. So it's got many of the features that we've seen. It's got the notion of a home agent, a foreign agent to home agent registration, care of addresses, and we'll see encapsulation in just a second. Okay, so I'm also, I'll tell you that in a second. All right, so there are three components to the mobile IP standard. Agent discovery, so how do you find a local or a foreign agent to help you out? The registration from the foreign agent to the home agent, and then indirect routing. So mobile IP takes an indirect approach. Okay, so remember we saw this before. This is just a slide from before. The mobile interacts with the with the foreign agent registers you at the home. Let's see how this happens in mobile IP. Okay, so I almost never put up packets, right? And actually, in getting ready for this class, I watched a couple of Phil's classes or your short videos, and I saw him put up packets. So I thought, oh, if he can do it, I can do it. Okay, so what's here is not important. What I want you to take away from this is that, okay, so what's the problem here? I show up to a network, and somewhere on this network is an agent who can help me, right? The foreign agent. How do I find a foreign agent? Well, there are already existing mechanisms for doing that. There's an icmp message, so you remember, hopefully you remember what icmp. They're sort of like control and signaling messages, right? So there's a icmp message that's defined. It's got, the only fields we really care about here are, well, this is going to be somebody saying, hey, I'm a home agent or I'm a foreign agent. I can help you out, right? So you join a network, you listen. These advertisements are being flooded to you, just like DHCP, right? And so you get one of these and you say, oh, here's a foreign agent that can help me out, right? So there's a bit saying I'm a foreign agent or I'm a home agent, and here's a bit that says, gee, if you wanna use me, you have to register, and we'll see some of these in just a second, right? So it takes standard icmp and has some extensions for mobility here. All right, so here's how it works. What's happening here? Here's me. I've just showed up in the Stanford network. I'm listening, and your friendly foreign agent in the Stanford network is broadcasting this and saying, I'm an agent. I'm a foreign agent. I've got some care of addresses that you can use. So here's me. This is my home address here. This is my mobile address. So I'm listening, right? I opened up my laptop right there. One of these things showed up. I say, okay, great. I want to register. So I say, this is the care of address I want. Here's my mobile address. Here's the address of my home agent. And how long I want this to, I want to hold this, and a sequence number and stuff like that, which we don't care about. Okay, so I send that, I get an advertisement. I send a reply. That reply is received by the foreign agent, who now registers me with my home agent. I should say there's sort of security that happens in here also in terms of needing to authenticate that actually it's me who's doing this to my home agent, and then a registration reply comes back. So pretty straightforward, right? Hopefully you've seen these kinds of mechanisms in something like DHCP. It's passed on to me. Okay, look okay? That's pretty simple. We see, there's a lot of internet protocols sort of discovery-based that look like this. Let's take a look at indirect routing. And let's now, we talked a little bit before about what the addresses are, but let's take a look. So here's I guess here's the destination, so I must be here. So this is, Mary wants to contact me. So Mary sends something to my home address, right? It's destined to me. This is maybe the only sort of interesting thing here. Let's look at what the problem is. Here's a packet destined to me. It's just an IP, standard IP datagram with the destination address in this network. Now this packet right here has to get over here. How's that going to happen? So you cover tunneling. In class? Okay, right. So if you've seen tunnels before, sometimes it doesn't get covered. So okay, so I'll just take a second because this sometimes blows your mind.
Reminding them certainly won't hurt.
Right, yeah, right. Right. Once you hear it 3 times, you really know it. And this may be just the second, right? So I've got this datagram that's addressed to me, but it needs to be delivered over here, right? But this is the datagram that I want and that I'm going to react to. So what does the foreign agent do? Well, think of Postal Service, right? This is just the equivalent of Mary or my mom getting this datagram, sticking it in an envelope, sending that envelope over here. That envelope will then be opened by the foreign agent who will take out this datagram and send it to me, right? So what we're going to do is we're going to send an IP datagram and we're going to wrap it in another IP datagram, okay? And so that's an example or an instance of what's called tunneling. So the packet, you can think of it, there's an IP tunnel from here to here, and what flows across that tunnel, right? So it's actually something addressed from here to here. What flows across there are datagrams within datagrams. So here's the IP datagram that was originally sent from here, and that's now encapsulated inside this larger datagram whose destination address is over here. Look okay? That notion of tunneling is used all over the place in the internet and actually in mobile cellular networks also to move packets of data from one place to another where they're destined. This is their ultimate destination, but you can think of this as an intermediate destination. Okay? That's sort of the most interesting thing here. It's delivered to me here. Whoops. And then I reply back, as we saw before. That's all I wanted to say about mobile IP. Any comments? Questions? Yeah.
So it seems NATs, like this all ends once you have a NAT, right?
Right, because
so like I have a mobile agent, I have a foreign agent behind a NAT, and suddenly my TCP connect, like that there's the NAT might be doing new mapping of my TCP port numbers, even if I had like
you don't even have a permanent address with a NAT.
Yeah, it just seems.
Yeah, so I wanted to say, gee, I don't think a NAT makes it that much harder because the NAT's just sort of, I mean, it's, yeah. I wanted to say that, but I realize that's wrong.
Yeah. I think it's just that your foreign agent's going to have to be a publicly routable address, and it's going to, you can't.
Right, so you've got to be able to sort of, do UPnP or something to actually go through the NAT. So, yeah, there are certainly issues there. I mean, one of the things I was wondering is if people were sort of going to bring up sort of Skype as an example here, which sort of doesn't sort of fit this mobile IP model because you're always going through sort of a point of indirection in Skype, often for exactly that kind of a reason, right? Yes.
How does last hop routing work once the packet gets out of the tunnel? Because the IP address is still kind of.
That's a great question.
Take a look at the gateway; it's going to send you in the direction.
What actually happens when you go from here to here? So I tell you what I think happens, especially if this is just, let's say there are no intervening routers here. Okay. When I send something from here to here, what's the outermost address that I use, right? When I send something from here to here, I actually send a link layer frame, right? So I take this datagram out, right? And I encapsulate that, or I put that inside an Ethernet frame. This is supposed to be old-fashioned Ethernet, an Ethernet frame that goes from here to here. So I don't have to worry about the IP addressing or anything like that here, right? Because what's sent out from here and received directly here is an Ethernet frame, and that Ethernet frame is just to the MAC address associated
ARP will take
here.
care of all of that.
Pardon me?
ARP will take care of all
right, exactly. But great question. Yeah.
Do you also have to? How do ICMP messages work? So.
You want to go back to this?
Oh no, I was saying with encapsulation. in this case? So you'd send the ICMP message back to what encapsulated it?
Whoa. An ICMP message, like if there were an ICMP message.
I was just curious. It seems as though you'd also need to. You can't preserve the same source as where the packet initially came from, right?
Sorry, this source address is down here, right? So the source address of the inner datagram is here.
Okay.
The source address of the outer datagram sent from here is the home agent here,
Okay.
right? So that's the tunnel from here to here. Does that answer your question?
Yes.
Oh, it does? I must have misunderstood your question, but if you've got the answer, that's great. Okay. Okay. All right. So this is what we've learned so far, and then I guess the sort of the very last thing I want to tell you about is mobility in cellular networks, just because it's in some ways it's the same and in some ways it's different. Okay, so you haven't covered cellular architecture here, okay? So this is just one slide showing you some important things here. The most important thing here are these things in the mobile cellular network called a mobile switching center. Okay, so we all know about towers. You know, do you have towers that look like palm trees here? You know, on the East Coast, we have towers that are dressed up to look like evergreen trees, and they look really bad. I can't. So are there palm trees? No. Okay, I'm very serious. On the East Coast, a lot of cell towers have branches that look like hemlocks, which is a kind of evergreen tree. All right.
Yeah, there are actually palm tree ones, but I think they're in Southern California. I've seen one.
Oh, you have?
I think I've seen one around here.
Okay.
We've got the evergreen ones around here, at least in Los Altos Hills.
Oh, you do have some evergreen ones? Okay. And, well, anyway, so a little bit off track here. You have cell towers. We all know about cell towers, right? So these cell towers connect to something called a mobile switching center, whose job it is to connect connect calls coming in through these base stations into the public telephone network. So we're not going to really. I'd love to come back sometime and talk about 3G and 4G data services and things like that. But we're just going to look at phone calls here. Okay, we're going to be very retro and not worry about data because we're really just sort of worried about how calls are routed and stuff like that. Okay, so you have these mobile switching centers, these MSCs. And their job is to connect some number of cells like this into the public telephone network, and these are the things that handle mobility, both in terms of being home agents and foreign agents. Okay, so let's whoops. Oh, that's a recall. So yeah, sorry, I could have just dropped that. Different cellular networks. So every cellular provider will have multiple MSCs. And yeah, okay, there's nothing too important there. All right, so in a sense, we have all of the mechanism and principles and everything we need to know to understand how calls are routed in a cellular network. Okay, so you've got the notion of a home network. We've seen that, right? A network that's your cellular provider. There's something there which is sort of almost exactly analogous to your home agent. That's your home location register, an HLR, a database in your home network, containing your permanent cell phone number, billing information, all that kind of stuff about you. Okay, it's a database. Actually, I got an email from, I think it must have been Jennifer Whittam, who's doing a database MOOC course. So I signed up for the MOOC version of this course, and because I did that, I got an email from Jennifer saying, "Take my database course because databases are everywhere, especially in networks." And she's absolutely right, right? And so here's a good example. There are lots of databases and networks. So there's a home location register in your home network. You're going to visit a network, right? So you go from AT&T to Sprint, and you're actually in somebody else's network. There's a visitor location register. It's also a database, and it's also in the MSC, and it's exactly analogous to what a foreign agent is going to do. We'll see that in a second. Okay, so you might think, oh, mobile IP, cellular networks, what do they have in common? A lot, right, in terms of just general structure, slightly different vocabulary. Okay, so routing's done indirectly. So here's a call that's routed to you. Let's say you're sort of down here somewhere, right? So the call goes to the MSC in your home network. The home network MSC knows you're not there. How do you think that happens? how does this HLR, home location register, how does it track the fact that you're not there? Do you think? Yep. So yes, so long as you take off the IP part of it. Remember, we're talking about phones now, but it's exactly what you say. I turn on my phone here, and my signal is going to be received here, and so there's going to be a signaling protocol that's actually going to go to the MSC, who's going to now signal back to my HLR and say, oh, you know what? Jim just turned on his phone inside my cellular network here, right? So it's exactly the same. Instead of looking at ICMP messages and router discovery, it's sort of the mobile equivalent to that. You open up your phone, there's signaling that goes on between your phone and the MSC where your information is gathered, and then this MSC will tell this MSC this is where you are. Also, this MSC will update its visitor location register. That's just like the foreign agent in a visited mobile IP network, right? So exactly the same kind of stuff. All right, so this HLR has been updated. The home MSC consults the HLR, gets the roaming number. So it's sort of the equivalent of your care of address, routes the call there because it knows this HLR points here, and then it's routed to you. Okay, so no rocket science here. We've seen this. Well, actually, this came first, I guess I should say, before mobile IP. All right, now something that the cellular network.
Can I ask you a question about that?
Oh, sure.
So if it's going through the intermediary, the source knows of the destination because you're phoning a remote. If you're phoning a foreign country, you get a ringtone that comes back from the far end. But do you know how that works? So presumably this works internationally. This is how it's done internationally as well.
I think it's the way it's done internationally also, right?
So then there is knowledge back at the source somehow. Maybe it's just through.
You mean whether or not this is local within the U.S. or it's in the U.K. or France, or?
So if you're phoning from the right to somebody who is international.
All right. If I'm calling
who's
here.
Moved internationally, they've just got off a plane in another country.
Yes. Right.
You will get the ringtone of that country when you.
Yeah. Right.
So how is. Now that's actually being played from that remote.
Yeah. So now I'm going to have to try to remember my SS7 signaling, but I think actually the ringtone is one of the very last things. So there's sort of, these are basically call setup messages that arrive here.
Okay.
And there's some handshaking, and one of the very last things that happens is actually you get a ring from one end to the other, and I think at that point you already know, you've got sort of location information, right? Wow. Okay, good question. All right, so the last thing I want to talk about here is handoff, because we talked about this earlier here, smoothness, one of the uninterrupted flows, right? And we saw that in mobile IP, I made this sort of big thing about, packets get dropped, who cares, right? Because TCP will recover from it, or if you do UDP, you deserve what you get, or you get what you get, and everything's fine. In the phone network, that's not quite true, right? Because there's this notion of a circuit, and the circuit should follow you, the circuit should be smooth, and have all of these good things about an uninterrupted flow. So we're going to see that here, in a cellular network, this notion of handoff is a little bit trickier than in the IP, or maybe a little bit more complicated. So let's just take a very simple case where I want to go from one base station to another base station, cell tower to cell tower, and that they're both within the same MSC. Okay? So the handoff goal is to route a call via a new base station without interruption. Why do I want to do that? Well, you know why, right? Maybe I'm closer to this one, stronger signal. Maybe this one, maybe actually I'm a little bit closer to this one, but this one's got all of its channels being used, and this one's free, so maybe the best thing to do is actually to hand me off to do some kind of load balancing. Okay, so there's a whole bunch of reasons why I might want to do that. So let's see how this is done. Okay. It gets way worse than this, but I'm not going to show you it. Because, look, this is all within one mobile switching center. Now you have to worry about the case that the mobile switching center is within the same network, and you're now switching between MSCs, or you're going to a completely new network. It gets really ugly. But this is ugly enough, okay? Because we just want to sort of get a feel for how handoff works. And where the intelligence is here. Okay, so what happens here? Step one, first of all, it's being initiated by the base station. So the base station signals the mobile switching center and says, hey, I'm interested in doing a handoff, and here are a set of base stations that I could hand off to. Now where does that information come? How does this base station know where to hand this car off to? Well, this car is actually passing information about base station scene. Okay? So you maybe read in the press about, tracking people from the kind of information they report actually to this base station. It's a lot richer than just, this is the base station I'm associated with. Okay, so anyway, on the basis of that information, this base station says to the MSC, I want to do a handoff. The MSC, remember, we're routing calls now, so we're switching circuits. This MSC says to this base station here, the new one, so this is step 2, says, okay, I'm going to allocate a circuit from here to here. This new base station then allocates a channel over the wireless from here to here. That's step 3, so that's actually allocated. It's not used yet. The base station here signals back to this one and says, hey, I'm ready. Right? So you've got this base station knowing there's going to be a handoff, this base station knowing there's going to be a handoff and having allocated all of the resources. Okay, so that's step 4 all the way back here. Step 5 is the old base station says to the mobile, you're going to be handed off now. The mobile and the new base station signal each other to open up that new channel. And then finally the mobile signals back via this base station through the MSC that, okay, handoff has been done. The MSC then says back here, handoff complete. Okay, so it looks a little ugly, or maybe not ugly, just sort of complicated, but maybe logical about what happens. Again, it gets much more complicated if there's multiple MSCs or you're switching into another carrier. But this should give you some of the idea about this. Notice what you're doing. This is called make and break, right? Because what you do is you first make this new connection, and then you break this one here. And in the case that you were doing IP or things like that, you can then think about, I should multicast stuff so that it goes here and it goes here. And in the IP world, it actually gets even a little bit more interesting. But
Jim,
that's for some time later.
We're actually out of time. Are we finished?
We're all done, actually.
Yeah.
So this is the ugly case. Sorry. One of the things I absolutely know I shouldn't do is keep students any later than class is over. So anyway, this is my next to last slide. We've talked about, so that's it, right? The things that I wanted you to remember were those 3 principles. We looked at mobile IP. We looked at the about the cellular network. I should say, what about higher level protocols, right? Say with mobile IP, logically you'd say, those are upper layer protocols. It's all invisible, right? TCP and UDP can and do run over wireless, no problem. The answer to that is true, but there are performance problems, and maybe that might have been, I'm not sure, maybe other people had come and talked about that. We have packet loss and delay over wireless that you learned in an earlier class, and some of the problems associated with that. Okay, so that's it. So, I tell my students, I hope they remember 3 things. I hope you remember 5, okay? We'll see. So let me just say, that's it. So let me just say thanks. I really appreciate the opportunity to come and visit here and give a class. I know it's the book's just a recommended, not a required textbook, but if you've got the textbook, I don't care how you got it, right? If you've got a copy of the textbook well, I shouldn't go on telling stories. I'll give you a data point, right? I asked my students in my class, how many of you bought the textbook? And the answer was about 10%. And I said, well, so a lot of used books, right? And then another 10% said, I got a used textbook. And the others were willing to admit that not which, it was one of two conditions. Either they didn't buy a textbook or they'd found one online. So anyway, I don't care how you got a textbook. If you've got thoughts about the textbook, I'd love to hear from you. You know, just like faculty like to hear from students, people who write textbooks love to hear from people who use them if you have ideas about what works.
Oh, that's fine. Don't worry about it.
And what doesn't? Okay. Also, I don't know how many of you use this, but one of the things that I did in my free time was to start developing an online textbook, and the first chapter is online. And I'm actually very interested in. Yeah.
So everyone knew about that in class.
Oh, okay, great. So if you have any comments on that, especially like, oh, here's a really cool new feature that would be great to have in an interactive online textbook, that I'd really, really love to hear about. I've actually gotten some really inspiring ideas from people about new things to add to an online textbook. So anyway, my apologies for keeping you 5 minutes late.
Thank you very much, Jeff.
Thanks again.